All right, welcome to the next video, final video for Unit 1. Not that the units really mean all that much, but today we're going to be talking about Topic 8, which is on valence electrons and ionic compounds. Couple of pieces of good news. Number one, this should be mostly review for you all. Definitely if you took me last year, if you had me as your teacher last year, a lot of this is going to sound familiar, especially as we get towards the end of the video. And then another piece of good news, this video shouldn't be that long, and the problem-solving video is going to be pretty short. So, yeah, some good things to look forward to here. But let's go ahead and get started. Okay, so the learning objective for this topic is for you to be able to explain the relationship between trends in the reactivity of elements and periodicity. We're going to be getting into a bit more than this, but at a fundamental level, this is what we're going to be talking about today. Okay, table of contents. We're going to be talking a little bit about valence electrons again. Actually, valence electrons are going to continue being important for many months to come. We're going to touch on ionization energy and electron affinity. Talk about ions and ionic bonds, okay, predicting ion formation, and then ionic compound nomenclature. Some of this stuff here at the end is where many of you all are gonna you're gonna recognize a lot of what we talk about. And then in the problem-solving video, I'll just do some simple naming of ionic compounds and actually determining of ionic compound formulas as well. Okay, so let's talk about this nice little picture I have here. Let's talk about valence electrons one more time. So you'll recall from the last video that valence electrons are the electrons in an atom that exist in the outermost energy level of that atom, in its ground state, of course. And the core electrons are the ones on the inside, or the inner electrons, not the ones on the very outside. So if we look here at my periodic table, right, that doesn't have the transition metals, but it does have what are called the main group elements in the first four rows. Okay, so group 1, group 2, technically this would be group 13, 14, 15, 16, 17, and then 18, right, all the way on the right-hand side. What you'll notice is that elements in the same group have the same number of valence electrons. And we already sort of knew that when we were looking at electron configurations. We recognized, right, that the final electrons in these two groups both ended in the s orbital, right? So like this is 1s1, this is the 2s1, 3s1, 4s1 electron, and so forth. So this was called the s block. And then these elements over here, their final term in the electron configuration was p, right? So like 2p3, 2s2, and then 2p1, 2p2, 2p3, and so forth, okay, all the way to 2p6. The implication of that then is that elements in the same group have the same number of these valence electrons, okay? And that's really useful for us, okay? What this means is that we can just look at the periodic table, look at where an element is, and determine the number of valence electrons it has. The only exception to that is helium, right? Helium is placed over here in the noble gas column for good reasons, but helium only has 2 electrons, right? Like if you look at helium here, there's only 2 electrons, right? It's only atomic number 2. So it obviously does not have 8 valence electrons. So that's really what this says here. Just summarizes what I just talked about. The elements here in this middle section are referred to as the transition metals. Technically speaking, they also have 2 valence electrons. Okay, so like this number 2 really does kind of permeate here all the way to the end of the row. However, we're not really going to be using the fact that they have 2 valence electrons due to the d orbital electrons that are present. We're going to perhaps talk a bit more about that later in the course. I'm still myself trying to figure out how much of a big deal it is that we have to make about that in AP. suffice to say, transition metals tend to not follow the same types of rules and patterns that these other main group elements do, due to the fact that they have these d orbital electrons. Okay, so let's also bring back some of the things that we talked about in the last couple of videos: ionization energy and electron affinity. So ionization energy, once again, is the amount of energy required to remove an electron from a gaseous atom, right? More ionization energy means it takes more energy to remove an electron. Lower ionization energy means it takes less. What that means, right, is that a high ionization energy means that those electrons are tightly bound. A low ionization energy means that they're not. Electron affinity, I didn't talk about this in the previous video. I wanted you all to sort of explore this for yourself. But electron affinity is kind of the opposite of ionization energy, right? It's the energy change associated with the addition of an electron, okay? And there are some terms here that I'd like to just go over really quickly. We're going to see these terms pop up periodically throughout the course, so it's good to just sort of try to get a handle on what these terms mean right now. So when we talk about electron affinity, right, it's the energy change associated with the addition of an electron. If an electron affinity is endothermic, that indicates that energy is required. You have to put energy into the system in order for that atom to acquire the electron. It's not going to do it on its own. And you can think of this as being an unfavorable electron affinity, okay? On the other hand, an exothermic electron affinity indicates that energy is released from the system. So when a atom gains an electron, it actually gives off energy. That's a favorable, energetically favorable situation. So endothermic, exothermic mean opposite things, okay? The way I remember this is that endo, this prefix here, kind of sounds like into, right? And so you have to put energy into a system in an endothermic situation. Exo kind of reminds me of the word exit, and that means that energy is exiting the system, okay? That's kind of how I remember things. But yeah, so if you can think of it in that way, energy has to go in, that's unfavorable, right? Energy comes out, that's favorable. Okay, so we didn't explicitly talk about electron affinity trends, but we're going to do so right now. So as you go from left to right across the periodic table, right? Let's think about ionization energy, right? As you go from left to right across the periodic table, the ionization energy went up, right? It was harder and harder to remove electrons from atoms, right? And that was due to that increasing effective nuclear charge while staying in the same valence level, right? So the distance away from the nucleus wasn't changing, but the amount of positive charge in the nucleus was going up, and so it was harder and harder to rip those electrons away as you went from left to right across the table. Well, let's think about what that would mean for electron affinity then, right? And don't pay attention to these words increases, okay? Because that's not actually going to help you, all right? What I want to think about is as you go across the period, or as you go across the row, does electron affinity become more favorable or unfavorable? In other words, let's say we're all the way over here on the right side of the periodic table, right? Are these elements like naturally going to gain electrons, like take on extra electrons, or not, right? Are they going to do it and then give off energy, right? That would be sort of a favorable situation. Or are you going to have to put energy in order to make them do that? That would be unfavorable, right? Well, think about that effective nuclear charge, right? Let's say I'm fluorine, chlorine, or bromine right here. These guys have relatively high effective nuclear charges, right? It makes sense to me that they would sort of favorably grab onto extra electrons, right? If they're out there, they'll just snatch them right up, right? And that's true, okay? Think about over here on the left-hand side, right? Lithium, sodium, potassium. Are they going to be favorably grabbing extra electrons? Probably not, right? If we take a look back here, lithium, sodium, potassium, that extra electron, where would it have to go? Well, it would have to go into this outer energy level, right? And it's far away from the nucleus. There's not a whole lot of effective nuclear charge over here on the left-hand side, right? Effective nuclear charge is higher over here, right? These elements here have larger numbers of protons than these do, as long as we're talking about the same row, right? And so, yeah, it's energetically unfavorable, right? You would have to sort of help them along. You'd have to provide them with some energy in order for that to happen. So that's the trend with electron affinity, okay? Is that it's more favorable on the right-hand side, less favorable on the left-hand side. And then you can use similar types of thinking with the group trend, okay? As you go down, and this is a bit easier to think about, okay? As you go down the periodic table, the elements are getting larger and larger, and that place that electron would have to go is farther and farther away from the nucleus, right? So it would be less and less favorable, right? More unfavorable. The further down you go, right, the bigger the atom gets, it would be less and less favorable, right, for that electron to be added. But as you go up the periodic table, right, you're getting closer and closer, it would be more favorable, okay? And so that is the trend, all right? It's more favorable in a left to right direction and less favorable in a top to down direction. And that's summarized over here. And here's an important note, okay? Try not to worry right now about the actual numerical value of electron affinity. If you read in the book about electron affinity, there's some quirky things with positive and negative signs. If you can avoid it, right, try to just think of it in terms of favorable versus unfavorable. I think that's going to be better for all of us in terms of understanding the concept, okay? Okay, so how exactly does ionization energy and electron affinity relate to each other, okay? Well, I'm just going to read this here. It says the general trends for ionization energy and electron affinity are the way they are for similar or really the same reasons, okay? It has to do with effective nuclear charge and distance from the nucleus that ultimately determine how attracted electrons are to the nucleus of an atom, right? If you're talking about elements in the same row, it's the effective nuclear charge that determines the difference, right? And if you're talking about elements in the same column, it's sort of the size of the atom, aka the distance from the nucleus, that determines their properties, right, or their behavior. So, in nature, when atoms interact with each other, okay, and I'm down here, the implications of this, the fact that ionization energy and electron affinity, the fact that different elements have different properties, right? Certain elements it's favorable, certain others it's not. What this leads to is the ionization of atoms in reality, in nature, okay? Electrons, due to the relative forces that they experience from nearby nuclei, can just move, okay? They're going to do what is energetically and really electrostatically favorable for them, right? If they are, so let's look at this example here, right? We have a sodium atom and a chlorine atom. These elements are both in the same row, row 3. Sodium has 11 protons, chlorine has 17, right? So you can see the physically larger nucleus here, right? Now this isn't drawn to scale, but it's good enough for what we're talking about right now. Sodium has this one valence electron out here in its third energy level. Chlorine also has electrons in the third energy level. It has 7, okay? So there actually is a spot where an electron could go. If you were to look at the orbital diagram for chlorine, its very last orbital, the 3p orbital, there would be an empty spot there for one more electron. So consider yourself to be this electron, right? In both situations, right? Let's say you're here in sodium, or let's say you're here in chlorine. In both situations, you're equally as distant from the nucleus, right? You're in the third energy level, right? And in both cases, you have the same number of core electrons that are shielding you or repelling you away, right? What's different, though, is that chlorine just has a bigger well, it has a larger amount of positive charge in the nucleus, right? 17 protons here compared to just 11. So which nucleus is going to pull harder on this electron here? It's clearly chlorine, right? So, and the fact that there is a spot for that electron to go, I mean, that's important, right? If this had been, say, argon, for example, the next element larger, which has a full third energy level, then this electron couldn't go there, right? And so then we'd be talking about a bit of a different scenario. But anyways, I don't want to lose our train of thought, right? So what happens in nature, if sodium atoms interact with chlorine atoms, the electron from sodium, the valence electron, will just hop right over, okay? And that is called ionization, right? Ionization is turning from a neutral atom into an ion, right? That's what ionization is. And so remember that ions are just atoms that have non-zero charges, right? And that happens when electrons move or transfer between atoms, okay? So let's keep talking about this scenario here, okay? When that electron from sodium moves over to chlorine, what we end up with are ions, right? One of them is actually positively charged now, and the other is negatively charged. Sodium lost an electron, okay? So sodium lost a negatively charged electron. In math, that's the same thing as subtracting a negative, right? And that actually means like addition, right? You can actually calculate, right, how positive this is. Sodium has 11 protons, but only 10 electrons, right? So its overall charge is positive 1. And then by the similar logic, right, chlorine is going to have an overall charge of negative 1, right? 17 protons, 18 electrons now, okay? When you create these ions through this process, one positively charged, one negatively charged, well, now you have a positively charged object and a negatively charged object, right? These two different ions. They are attracted to each other, okay? They will, in essence, sort of stick to one another, right? And that's called an ionic bond, okay? And we're going to talk a lot more about bonding and how this all works at a later date, okay? But for today, we're going to just sort of stick with that, that is sort of how ionic bonding happens in the first place, right? It's due to the electron, what it feels, where it goes, and then the resulting ions that exist as a result of that, okay? Together, this pair of ions, and it can actually be more than two atoms, okay? This process can happen, with more than just two atoms present. This resulting unit is called an ionic compound, okay? One important thing I want to mention about ionic compounds, okay? The overall number of protons and electrons in this system has not changed, okay? So we started with a neutral sodium atom, a neutral chlorine atom. We still have a neutrally charged system, okay? And that is important. All ionic compounds are neutrally charged, okay? Even though we have a positive aspect and a negative aspect, right? We've got the positively charged sodium ion and the negatively charged chloride ion or chlorine ion. The overall system here is still neutrally charged. That is very, very important, and I'm going to be bringing this up several times in the future, okay? But if you are taking notes at home, make sure you write this down, okay? All ionic compounds are neutrally charged, and underline this 15 times. Very, very important. Okay, so let's talk about how we can sort of predict which type of ions exist. Okay, it's actually really, really easy, and this is where we're getting into some of the content that a lot of kids are going to remember from last year in your first year chemistry course. So generally speaking, we can use patterns on the periodic table to predict which types of ions form in nature. All right, generally speaking, okay, elements with few valence electrons tend to lose them, while elements with many valence electrons tend to gain them. Think back to this example here, right? Sodium only had one valence electron, chlorine had 7. Now, this is a generally true concept, okay? It is important to remember, okay, that ultimately the electrons do what they do, Okay, the electrons behave the way they do. They transfer from one atom to another due to the electrostatic forces involved. Coulomb's law, effective nuclear charge, distance from the nucleus, etc. Okay, what I'm talking about here is just a general trend or pattern on the periodic table. Okay. In both of these cases, right, with elements that lose electrons and elements that gain them, the resulting ions usually end up adopting the electron configuration of noble gases. Okay? Meaning that in their valence level, they end up having 8 electrons. Okay? And their electron configuration looks like this, right? Ns2, Np6, where N is the outermost energy level, or that valence level, right? So 2s2, 2p6, or 3s2, 3p6, that sort of thing. So, so over here on the right-hand side, this is generally what the electron configuration looks like in most ions, all right? Not always, and in fact, when you get to like the transition metals, it does not look like this at all. But for main group elements, this tends to be what the ions end up looking like. Okay? All right. I do want to say a few more things about noble gases specifically. Okay? So if we take a look at noble gases, right, they have these sort of full valence levels, right? The 1s2 orbital is full here. The 2s2, 2p6 orbitals are full. Same for argon and krypton. As a result of that, okay, many noble gases tend to be very, very hard to ionize. Okay, it's very, very hard to take electrons away or to add electrons to them. Okay, their valence level electron orbitals are full. What that would mean, right? So let's talk about electron affinity, right? You're trying to add an electron. Adding a new electron to a noble gas is very difficult, okay? Because that new electron would need to be added to a new, farther away electron orbital, right? Let's take a look here. If you're trying to add an electron to neon, well, it can't go into this second energy level, right? 2s2, 2p6, those are full. So that new electron would have to go into the third energy level, which is pretty far away compared to the other energy levels. And so that electron is not going to feel a very strong attractive force to the nucleus, and it ends up being sort of an unfavorable process, right? You'd have to put energy in order for that electron to sort of go into that atom. And it's similar when you talk about the ionization energy, taking electrons away, okay? Noble gases tend to have very, very high ionization energies, and that is due to the fact that noble gas elements have relatively high nuclear charges, right? They're on the very right-hand side of the table, which means that their electrons experience relatively high forces of attraction compared to other elements in the same row, right? So it's difficult to take those electrons away. Once again, right, if you read that final sentence down there at the bottom, it all boils down to those electrostatic forces. Coulomb's law, effective nuclear charge, distance from the nucleus. Those are the fundamental ideas that you need to be thinking about whenever you're asked about questions on ionization energy, electron affinity, okay? All right, let's move away, finally, from the difficult concepts of electrostatic forces, okay? A lot of you guys are really, really going to like what we're about to do here, because what we're about to do is we're going to learn some rules. That's what nomenclature is, right? Nomenclature are just sets of rules that you use to name things, okay? And this is what a lot of you all should really recognize from last year. I'm sure you did this in your general chemistry, or in your first year chemistry class. So, predicting the ionic charges on elements is relatively easy using patterns on the periodic table. Let me be very explicit, right? So, these elements over here in the first column, they are generally going to lose that one valence electron, right, due to the electrostatic forces, right? That electron is more than likely, when it interacts with another atom, it's more than likely going to hop off and say, see you later, I'm going over to this other electron where I can be closer to the nucleus, for example, right? As a result, okay, hydrogen, lithium, sodium, potassium, these first elements here in the first column, they are going to adopt a positive 1 charge, right, because they are losing a negative electron. Likewise, elements in the second column, beryllium, magnesium, calcium, they're going to adopt a positive 2 charge, right, because they're going to lose both these electrons, both these valence electrons. And then the same thing applies for like boron, aluminum, and gallium, right? 3 valence electrons, they would lose those electrons and adopt a positive 3 charge. I'll talk about the fourth column here in a second, but then you can sort of apply a similar sort of process here for these elements here, 5th, 6th, and 7th columns of the main group elements. Fluorine, chlorine, and bromine, these guys each have a spot, one spot for an additional electron in their valence level. They're going to take an electron if it's available due to those electrostatic forces once again, right? And so they're going to end up with an overall charge of -1, right? Because they're gaining one negatively charged electron. These guys would end up with an overall charge of -2, and these guys would end up with an overall charge of -3, right? Because they're adding 2 or 3 electrons respectively. Now, this group, carbon, silicon, germanium, you're sort of in the middle of the road here. So you're almost like at a fork in the road. They've got 4 valence electrons. One could argue that maybe they would lose these 4 valence electrons and form a positively 4 or a positive 4 ion, right, by losing 4 negatives. You could also potentially argue, oh, well, maybe they would add 4 electrons, right? In which case they'd have a -4 charge, right? They'd be a -4 ion. Well, in reality, sort of both of those things can happen, and in reality, this doesn't happen as often as it does for these others, right? So like lithium ions are super easy to form, carbon ions not as much, right? So these elements here, and a lot of these elements tend to form what are called covalent bonds. We're going to get into that later, where the electrons aren't jumping ship completely. Okay, we'll get into that later. But long story short, elements here in this fourth column, you can't really predict what type of ion they're going to make, right? With elements on the left side, right, they're going to lose those electrons. Elements on the right side, they're going to gain them. Here in the middle, it's kind of a tough call. So yeah, and then I also just talked about noble gases. These guys aren't going to form ions at all, generally speaking, for the reasons I outlined. Okay, so you can predict the ionic charges based on where an element is. Naming the compounds that are formed by ions is also relatively easy. Okay, so a couple of definitions here. Cations are positively charged ions, so these would be atoms that have lost electrons. Anions are negatively charged ions. It's getting very dark outside. Turn my lamp on there. Sorry about that. Anions are negatively charged ions. These would be atoms that have gained electrons. Ionic compounds are always named with the cation first and the anion last. Okay, always. All right, and this is what I said about you guys are going to like this. A lot of you all really like rules that you can follow, and so this is one of them. All right, the cation, the positively charged ion, retains its elemental name. Okay, while the anion, the negatively charged ion, adopts the suffix IDE. So just to give you an example, back here, this ionic compound would be called sodium chloride. So chlorine would change from chlorine to chloride, right? You would change that suffix or change the ending part of chlorine into IDE. The specific rules on like what all of the suffixes or what all of the anions are called, that can get a little hairy. Like oxygen turns to oxide, nitrogen turns to nitride. Those are things that you'll just sort of pick up over the weeks and months that we spend in the course. Okay, a few other things that deal with naming. Some more rules. Not all ions that exist in nature are monatomic. Okay, what that means is that not all ions are made of single atoms. Okay. There exist these things called polyatomic ions, and I'm sure that if you've had chemistry before, you've heard of these. Okay, polyatomic ions also exist, and these are made of several atoms together. We're going to learn more about the structure of polyatomic ions and sort of why they exist later in the course. But for now, you need to start learning, and by learning I mean memorizing, their names and formulas. Last year in my class, I provided you with a sheet that had the different polyatomic ions on it, and you were allowed to use that on tests and quizzes. You're going to be expected to know these on the AP Chemistry exam. And if and when we return in person, this will be one of the very first things that I assess you on, okay, is your knowledge of the polyatomic ions. I've got a link to the polyatomic ions here in the slides, and I've also added a link to polyatomic ions that you need to know in the reference materials on Canvas. I'll just pull this up really quickly. Here are the polyatomic ions I'd like you to know. I also have a link here to a one-page document that has some tips for how to best learn these. I would advise checking that out if you're going to attempt to try to memorize these, which you need to, not necessarily right this moment, but over the next weeks and months you do need to learn those ions. These polyatomic ions have specific names which don't change when found in ionic compounds. Okay, so treat them, treat polyatomic ions just like monatomic ions. The only difference there is that you don't really have to do anything if it's the anion, right? If it's a negatively charged polyatomic ion, you're not going to add this IDE suffix. A lot of times they already have an IDE suffix. Sorry, I should rephrase that. Sometimes they do have an IDE suffix, but actually a lot of times they don't. They have their own sort of suffix like ate or ite or even something totally different, okay? All right, one last thing on nomenclature has to do with transition metals, okay? So another quirk in the nomenclature rules comes up with dealing with elements that aren't found in the main groups. So the main groups are the two groups over here on the periodic table, 1 and 2, and then like the S block, and then the P block elements, right? So 13 through 18. Those elements follow nice rules, okay? The elements in the middle, the transition metals, these can get a little bit hairy, all right? So they need special treatment when named in an ionic compound, all right? So let's look at a nice easy example. So this is a formula for an ionic compound, KF. Potassium and fluorine are both main group elements, so we can tell what charge they're going to have, right? If I go back here to my periodic table of models, here's potassium. It's going to lose that 1 electron, so it's going to have a positive 1 charge. Here's fluorine. It's going to gain 1 electron to have a negative 1 charge. Okay, so positive 1 charge, negative 1 charge. That means the overall formula here, KF, would be overall neutrally charged, right? Positive 1, negative 1, those would cancel each other out. And the name for this one would just be potassium fluoride. Okay, potassium fluoride, IDE suffix there. Okay, so that's easy. Okay, let's look at this one. FeO. Okay, let's talk about oxygen first. All right, oxygen is a main group element. All right, it is located here. It's got 2 spots for electrons, okay? So usually oxygen is going to adopt a negative 2 charge. It's going to gain 2 electrons. But what about iron? Okay, so we have a negative 2 charge here. What about iron? Well, ionic compounds are always neutrally charged, okay? So what that means is that the iron, cation, must have a positive 2 charge. Okay, that's true, right? So if we see the formula here, we don't know what the charge on iron would be just by looking at the periodic table because it's one of those transition metals, right? So it's not in one of those nice rows where we can follow the patterns on the periodic table. It's in the middle, so we're not sure. But when we see this formula, we can determine that it will have a positive 2 charge. But what would its name be? Are you thinking iron oxide? Because that is false, okay? And here's the trouble, okay? The problem is iron actually has the ability to adopt several different ionic charges, okay? Not all iron is going to have a positive 2 charge. Iron can have like 7 different ionic charges, In fact, some of them can be negative. It can have a charge of like +2, +3, +6, right? So that's why the transition metals are a little bit messy, okay? So to deal with this, right, the convention is to use Roman numerals to differentiate between the different possible iron ions, okay? And so what I'm talking about is in the name of the compound, you use a Roman numeral to differentiate between the different types of iron ions. In this case, the name would be iron 2 oxide, where the Roman numeral 2 represents the +2 charge of the iron ion, okay? And obviously we're going to get plenty of practice with this, so don't worry too much if you are not getting all of this right this moment, okay? I just wanted to show you, here's another version of iron oxide. Okay, it's called iron 3 oxide. This is a distinctly different compound. Here's pictures of them. This is iron 2 oxide. This is iron 3 oxide. They are different, okay? They have different properties. They have different colors, right? So it is definitely something that we have to pay attention to. They even have different formulas, okay? Remember, ionic compounds are always neutrally charged, right? So if we have iron with a +3 charge and then oxide, which is going to have a -2 charge, it can't just be a 1-to-1 ratio, right? The formula here would have to be Fe2O3, 2 +3s for an overall charge of +6 in the cations, and then 3 -2s for an overall charge of -6 in the anions. Okay? All right. That is it for the end of the notes here. Like I said, the problem solving video is going to be pretty short. I'm going to be working through these example problems. And like I said, hopefully a lot of this is review for you guys. I know it definitely is for some of the kids I had last year. We did all of this nomenclature stuff in class. So, and most of your problem set problems are going to be on this type of nomenclature because it is important it's like a foundational building block of chemistry moving forward. So anyways, thanks for watching, and I'll see you in the next video.